Hello, a very good afternoon to one and all. Is this audible? Is my voice audible?
Yes, sir.
Yes, sir.
Can you see the presentation?
Yes, sir.
Yes, sir.
Sir,
Can anyone read the first line and the second line? First
Professional active on information theory coding, unit 2, information channel.
information. Okay, right. Thank you. From this, I had understood that you are able to see my presentation. So in today's class, we are going to start unit number 2, information channel. So with the outline of this unit 2, we'll be seeing these different concepts. The first concept is your binary symmetric channel, followed by mutual information. Then we'll be seeing a differential entropy, an extension to discrete memoryless source, channels, channel capacity, channel coding theorem, and the trade-off between bandwidth and signal to noise ratio. So to start with the introduction, in your previous subject called digital communication, you would have studied about different types of source encoders. like pulse code modulation, delta modulation, adaptive delta modulation, differential pulse code modulation schemes, where these systems had a channel encoder where the output would be given by a source encoder corresponding to the channel encoder. So in this system, the channel encoder had redundancies, which we call redundant information or errors in the form of binary information sequences. These redundant bits would have been obtained due to the channel's conditions like noises, interferences. Due to these two, redundancy will occur, and in turn, the redundant bits were being obtained at the receivers. So the output of these were fed to some modulator schemes, such as frequency shift keying, phase shift keying, differential phase shift keying, and many more, which we called in general as binary modulators. Or they are used in other type of modulator segments or modulator systems like M arrays, PSK, M array, FSK, M array minimum shifting techniques. So at the receiver end, they had this type of demodulators and detection schemes in opposite to the modulator schemes. So in viewing this, the detector had two types of decision making. One is taking a hard decision, and second one is your soft decision. So what is this hard decision is that if we consider a binary modulation system where either binary 0 or 1 is being transmitted, a hard decision system was being implemented. In the case of binaries, zeros and ones, hard decision detector system was implemented. Whereas when the levels of the Q level, we call it as, or when they used M array systems, which is greater than 2, which is always greater than 2, there they had used soft decision systems in the detector. So this is what an introduction towards types of channel is. In that, the first channel is your binary symmetric channel. So what is this binary symmetric channel is? So the binary symmetric channel will have a value of m is equal to 2 in the hard decision. You can see what is a hard decision then. Hard decision is that transmitting binary zeros and ones. For that, an appropriate detector is being used such that we use only binary zeros and ones. So hard decision is used in a binary modulation system. So the name binary is being obtained. So m is equal to 2, having zeros and ones as interpretation. And the diagram which is shown here corresponds to an binary symmetric channel, which is composite discrete input and a discrete output in nature. We have an input sequences in the form of analogic. We have a corresponding channel encoder. We have a binary modulator, then channel, then the corresponding demodulation and detector scheme, which is hard type, hard detector. Then you have corresponding channel decoder and the output of the data. So this is what a generalized channel is, which is of binary. Since we are using binary modulator, it's a binary channel. So now, what do we call it as a symmetric? Is that the symmetric arises from the word that if each output, that is what in the output data, each output bit from the channel is depending upon only the input bit, we call it as symmetric. I repeat it again. If the output bit from the channel depends only upon the input bit, we call it as symmetric. So this channel is called as binary symmetric channel. So for that we'll see with a diagram. Okay, I'll explain this with a diagram. What is this binary symmetric channel is? So this binary symmetric channel is shown in the diagram. So we have two inputs. Since we have binary, two inputs, zeros and ones. 0 and 1 is your input. Output will be also binary 0 and 1. So now I consider the probability of error in the channel is p, small p. I write it as small p. Okay, small p I write it as. So when it transfers from 0 state in x, so x I am taking it as input, y I am taking it as output. So from x to 1, if there is a change, so change in the transition, so which I can call it as a probability of error. So I am writing it is being denoted as p. Okay, if x value is 0 and the output is 1, so there is an error, so denote it as p. And similarly, if x is equal to 1 and output y is 0, so there is an error, probability of error occurring, so I write it as p, so which you can see in this arrow mark. Okay, p. So when if it goes from 0 to 0, the state of x is 0 and y is also 0, it is 1 minus p. And if it is for x is equal to 1 to y is equal to 1, so then it is 1 minus p. Okay, so this is your necessary condition for binary symmetry. So with this state, it shows that I'll write these equations. So p of y is equal to 0, the probability of y is equal to 0 will be obtained on two different cases. When do we get? Is that when x is equal to 1, when x is equal to 1, y is equal to 0, which is a probability p. And another thing is that when do I get another probability p is that an error when p of y, which is this, p of y is equal to 1 and p of x is equal to 0. So in that case we get error, so which is p. So in what are the cases that we don't get error is that in the case of 1 minus p, if x is 0, y is also 0, so no error. Okay, so that is highlighted in the equation 1.32. P of y is equal to 1, x is equal to 1, it is 1 minus p. P of y is equal to 0 and x is equal to 0, it is 1 minus p. So this is your binary symmetric channel. So at last it's been given that the above two equations, these two equations represent a binary symmetric channel as shown in this diagram, which gives us that each output bit from the channel depends only upon the corresponding input bit. Hence, this channel is called as memoryless channel. So this is what a binary symmetric channel is. So this binary symmetric channel is a special case. It's a special case of memoryless channel. So where the input bits and output bits corresponds m is equal to 2. Okay, so this is a binary symmetric channel. So next is an important mutual information. So before going to the mutual information, let me check how many are present. So almost 17 are present. Okay. So this mutual information I'll show you here in the dashboard. This mutual information comes from the discrete, it comes from your information rate. Let me zoom it, which we had seen in the last class, information rate. Okay, is this dashboard visible? So it's a Jamboard. Is the Jamboard visible? Is the Jamboard visible? Let me check this not here. Vamsi, is the Jamboard dashboard visible to you? Vamsi,
Yes, sir.
is the Jamboard visible?
Yes, sir. Yes, sir.
Okay, okay, fine. So this was the last class yesterday's information basics where we had seen definition of information rate. R is equal to small r into h. R, capital R is the information rate, h is your entropy, and the small r is the rate at which the messages are being generated and measured in information bits per second. So from this we are going to derive this mutual information. Okay, we are going to see what is this mutual information is. Let me go back to the Jamboard. So as said in the previous slide, memoryless source or a memoryless system. So what is this we call as a memoryless is that if the output of any system depends upon the corresponding input, we call it as memoryless source. So a source whose individual output letters are statistically independent. In the sense it is dependent upon only on its input signals. So it is called as a discrete memoryless source. In such a source, the current letter is always statistically independent from all the past and future outputs. So this we call it as memoryless source. And we have another type of source also called discrete information source. The information which is said to be discrete are being emitted by only one symbol. Only one symbol out of the two. For example, if you have binary system, either if it is due to 0 or if it is due to 1 of any of the symbols, any one of the
Dinesh, good
symbols.
afternoon.
Good afternoon, sir. Good afternoon, sir.
How things are going?
Fine, sir.
Only strength is around 16 students.
Yes, sir. Because
Strength?
as elective paper, sir. Total strength 19.
Oh, information coding. Information
Yes, sir.
coding.
Yes, sir. Information theory and coding, sir.
Total how many?
19, sir. 19.
Oh, 19 is it? Okay. Okay, sir. Okay, carry on.
Okay, sir. So coming back to the discrete information source, the information source is said to be discrete when any one of the symbol, either the binary 0 or binary 1, from the finite number of symbols leads to the output of that corresponding system. So the output depends upon any one of the symbols. So this we call it as discrete information source. So coming to the next source, next type, two types of sources that are being used is a stationary source. I think you all are able to see this. Then I'll zoom in a bit. Stationary source. So if the output of the source is stationary, sorry, if it is statistically dependent on past and future outputs, the thing is that the output of the source will eventually depend upon the past and future outputs. So then that type of system or that type of coding, we call it as stationary source coding or stationary source systems. So an example is that English text is always stationary in nature. When you script something, the previous and the future can be easily scripted. So which is a best example. So next is analog source. The analog source has an output waveform x of t. For example, I consider x of t, which is always a random process. Okay. So the sample function of a random process x of t, if we use that type of system instead of digitals, either if you use digital, we write in terms of zeros and ones, either in the form of RZ, NRZ, you'll be writing written to zero, not written to zero. Representation is always in the waveforms with respect to x of t. Then this type of system is called as analog sources. So then how do we convert this analog sources into discrete sources is that with the help of sampling theorem. So sampling theorem plays a major role in converting the CT signals to DT signals. Okay, continuous time signals to discrete time signals. So there we will be converting them into appropriate signals and we'll be using it as an analog source. So these are the different types of source channels before which we have seen. Coming to the next is, I'll check where it is. Just I'll check mutual information. Just I'll check me. I had put an dashboard for mutual information. Just I'm checking on that. Wait a while. I'll check where it is. Mutual. Just a minute. I'll show you the mutual information nearby. So after the different types of channels, which you are going to see is mutual information. So I'll go back to the mutual information. So, mutual information. So this mutual information is obtained from two different sequences or two different messages which are having probabilities of occurrence. The probability of occurrences. If you have two different probability of occurrences, so what will happen is that we may get systems with two different equations. So if I am using two informations, for example, if I have x information, if I am having y information, so two informations. In the previous class, we had seen the information for only one variable. So now we'll see it about for two informations. If x is there, just a minute, I'll check where I kept my If you have a single information, it is easier to calculate the information, single variable. But if you have more than that, what to do? If you have two variables, if you have three variables, or if you have some m variables, for that I'll show you how to calculate information. Why? Because if I have two variables, if you take x is a variable, y is a variable, differently in two different cases, it is easier to calculate information. But when we take two informations together, x being an information, y being an information, then we need to see the mutual information of that. So that I'll show you. Yes, I'm working on the presentation only. Kindly await. I'm searching the file where it is. Kindly await. I'll show the presentation. Yeah, is it visible now? Is this visible? Any one of you can put it in the chat box.
Yes,
Yes, sir.
sir.
Okay. So the thing is that if you have a single variable, it is easier to calculate. So which is the first case that I'm showing you. If you have a single variable which is being used for a system, it is easier to give you the probability of occurrences. So in the first case, I consider a discrete random variable x with a maximum possible outcome ranging from uh, I is equal to 1, I is equal to 2 till I is equal to n. So I label it as xi. So the information for this can be easily calculated as information of xi, which is my symbol, which is equal to log of 1 divided by probability of xi, or I can write it as minus log of probability of xi. So this is in the case of a single variable, only a single variable is present x. So in the next, I'm going to consider two discrete random variables. If one is the case, you can easily write the information rate can be equal to, or the information rate I of x of I is equal to minus log probability of xi, or log of the base to 100 by probability of that x of I. So if there are two informations, or if there are two variables with outcomes differently, so I have an outcome of x is equal to xi varying from I is equal to 1 to n, and similarly I have y with an possible outcome of yj, j is equal to 1, 2, 3 till m respectively. So then what is my information rate? So this is what I'm going to show you. So this is case 1, so this is over. So in this second case, when two discrete random variables are being present or two messages are being present. We'll see that. So when there are two variables, we get two different cases. One is case 1, second one is case 2. Case 1 deals that x and y doesn't has information about each other. X doesn't have information about y and y doesn't have information about x. So in that case, we can directly write I of xi is equal to minus log of p of xi, and yj is equal to, so I of yj is equal to minus log of the probability of yj. So that is your first case under the two variables. And eventually in the second case of these two variables, we have, in the first case we are saying no information of x and no information of y are interconnected. Y doesn't has information of x and x doesn't has information of y, which is the case 1. So in the second case, we are going to see that two informations about x and y. X is giving information to y and y is giving information to x, or we can eventually say that x and y are fully dependent. The meaning is that y knows some information about x and x knows some information about y. Okay, x knows some information about y and y knows some information about x. So here we need to determine the information. So how do we determine information? Is that by this relation, which we call it as mutual information. So information rate of x is to y between x and y is always given as I of information rate of xi is to yj, which is equal to log of probability of xi by yi divided by probability of xi. This is in the case of x is to I. Probability of xi divided by yi, the whole divided by p of xi. I forgot to put a bracket, so you can understand. I have a whole bracket for the logarithmic function for xi is to yi. So next, if I want the mutual information between y and x, is log of logarithmic function of probability of yj divided by xi whole divided by probability of yj. So wherever I denote y, it is j. Some places you can not see it properly, I think so. It is j. Wherever y is there, it is j. Wherever x is there, it is I. So which can give you the information of I related to, so information related to yj is to xi. So this is what information of mutuality is concerned. Okay. I close this. I forgot to upload in the dashboard, or I think I would have left out somewhere. So no. This mutual information. So this mutual information I am going to write in terms of a continuous variable or in form of a continuous system, which can be given as I of x is to y is equal to, the limits varies from minus infinity to plus infinity of x information, and y also varies from minus infinity to plus infinity, function of xy, function of xy, logarithmic function of x by y divided by function of x with the limits dx and dy. So this is your mutual information in continuous variables. Okay, so where this function of x comma y is the joint probability distribution function, of x and y. F of x by y is the conditional probability distribution function of x, given that y is always equal to 0. So the mutual information will have some properties that is to be satisfied. So if these properties are satisfied, then mutual information can be determined or it can be measured, which is I of symmetric. I of x is to y is equal to I of y is to x. Then next I of x is to y should be always greater than or equal to 0, and I of x is to y is equal to h of x. H represents your entropy of x minus h of x by y, or in other terms you can write h of y minus h of y by x. So where this h of x by y or h of y by x is the conditional differential entropy. Conditional differential entropy. And now you will be getting a doubt, what is differential entropy? I know that, which we are going to see in the next topic. Conditional differential entropy. So consider a variable x. Now we consider a variable x having probability density function f of x of x. Then for h of x, which is a differential entropy, you can find the value ranging with minus infinity to plus infinity. F of x, which is function of x, logarithmic 1 divided by f of x into dx. So this we call it as uncertainty value of x in the order of infinity. Uncertainty in value in the of x in the order of infinity. So this is a similar equation to your entropy of a discrete variable. So this is your differential entropy. So differentiating it, the entropy whichever you got for x probabilistic function or for an x value, so that you are going to differentiate with the limits. So limits will be given, which ranges from minus infinity to plus infinity for a continuous random variable. So that we call it as differential entropy. And extension to the discrete memoryless source. Okay, previously at the beginning of the class we had seen discrete memoryless source. I think so, right? So discrete memoryless source is that the output of the channel is dependent upon on the corresponding input bits of the system or input bits to the channel. So in the same case, we are going to extend it a further by introducing entropies. That's all. So now consider the same source having x1, x2, x3, x4 till xn, so discrete memoryless alphabets having m, capital M number of individual symbols. So these symbols will occur in groups of two or more, minimum two. Minimum two. So that represents either your binary, starting from binary systems. Binary is equal to 2, ternary is equal to 3, quaternary is equal to 4. So these groups of symbols will produce another source if I introduce an alphabet with that, with m power n distinct symbols. With m power n distinct signals. Okay. Where n is the number of successive symbols in a group or in a block. So if that is the case, the entropy can be related as, if I have n successive symbols in a group or a block, the entropy, which is entropy of this alphabet, which is x of x power n, is equal to n times h of x. So this is how to relate the, or this is your discrete memoryless source extension. Extension is that we are going to add m power n symbols, where n is the number of successive symbols in that group or in that block. If that is the case, the total entropy will be n times h of x. Just a minute. Yeah, this is your discrete memoryless source extension. So far we have seen binary symmetric channel. We are seeing mutual information, right? Information, mutual information, a discrete memoryless source extension. Next topic is channel capacity. Channel capacity. So what is this channel capacity? So channel capacity is a simple thing resembling how much amount of information or how much amount of data or how much amount of uh, things that the channel can accommodate. How many? Somebody is asking the chat. Let me check it. How much amount of information that can be carried out through the channel is what determining channel's capacity. So capacity of that particular wide channel, wireless channel, or a binary symmetric channel, or a distortionless channel, whatever might be. So determining that is our major aim in information theory. Okay. So for that, we need to take your mutual information. So always the channel capacity is expressed in terms of mutual information, which is given as this: I of x is to y, summation I is equal to 1 to n, since it is x variables, and for y variable j is equal to 1 to m, probability of xi comma yj logarithmic to the base 2 probability of xi divided by yj the whole divided by probability of xi. So from this, first we will calculate what is this p of xi by yj. So this p of xi by yj is given as p of yj divided by xi into p of xi. So this is an equation which is predefined, and from this we can find p of xi by yj, so which is equal to p of yj divided by xi divided by p of yj. So take this equation number this which I'm highlighting, and substituting 1.1.32 which is given here. So then the equation will become I of x is to y, which is equal to summation I is equal to 1 to n, j is equal to 1 to n, probability of yj by xi, probability of xi into log to the base 2 p of yj by xi the whole divided by p of yj. So write it as label it as some equation which it's been given 1.1.34. So then this p of yj can be expressed in terms of another equation, which is this: p of yj is equal to summation I is equal to 1 to n p of yj divided by xi into p of xi. So then this equation will become this equation, which is what I of x is to y, summation I is equal to 1 to n for m, summation j is equal to 1 to m for j, so it's for y, not j, for y, probability of yj divided by xi into probability of xi log to the base 2 upper half as it is, probability of yj divided by xi divided by this probability of yj, summation I is equal to 1 to n, probability of yj divided by xi, probability of x of y. So from this, we can conclude that the mutual information of this transition probabilities can be obtained as an maximum average mutual information. You see this equation, this is your maximum mutual information. So this maximum mutual information that is obtained can be given as your channel capacity. So the channel capacity of any discrete memoryless channel is given as the maximum average mutual information. Maximum average mutual information. So this maximum average mutual information, maximum probability of xi, I of xi is to y. So this is channel capacity. Let me show you a Jamboard. So this is what your average mutual information is. You can go through that. The same information is what we are seeing. So average mutual information. The average mutual information can be obtained from the equation which you had seen just now. I of x is 2y, summation of I is equal to 1 to n. Summation j is equal to 1 to m, probability of xi, yj into information of xi, yj. So where I of x I yj is the weighted by joint probability function, and the p of xi is to yj is the overall possible joint events. So this we get as the maximum mutual information. This one, it is highlighted in blue color. Okay, just substituting the logarithmic function of information I. I think we had seen the properties of mutual information. I think we had seen this. So again, I'll explain, no issues. I'll explain it again. The mutual information of the channel is always symmetric, so which is I of x is to y is equal to I of y is to x. And in terms of entropy, I of x is to y is equal to h of x minus h of x by y, or h of y is equal, or I of y is to x is equal to h of y minus h of y by x. And the mutual information is always positive in nature, greater than or equal to 0. And mutual information in terms of joint entropy is this: I of x is to y is equal to h of x plus h of y minus h of x is x comma y. Nothing in the channel. So from this we can easily find the channel capacity. Here is channel capacity. Next is the channel coding theorem. So it is an important coding theorem which we are going to use. In unit 1 we had seen Shannon's first theorem. So in unit number 2 we'll be seeing extension of Shannon's first theorem, or we call it as Shannon's second theorem. So this Shannon's second theorem is purely meant for channel capacity measurement. So how do we measure this channel capacity, which you had stated in the earlier? So maximum rate of the information rate, or the maximum average information of the mutual information determined, is called as your channel capacity. So how do we obtain it? And how do we get that? Is that based upon this Shannon's second theorem. So the Shannon's second theorem states that it is always possible to transmit information from one place to another place with a rate R, capital R, having some probability of errors, having the rate less than or equal to C, capital C, where C is the channel capacity. Capital C is your channel capacity. So this theorem states that with a source of sequences of messages which is having m greater than or equal to 1. So message sequences greater than 1 normally. So which is your binary or ternary or quaternary and so on. So having information rate R. Okay. So for this, what do we define is that R less than or equal to C. If this is being satisfied, Shannon's second theorem is satisfied. With the R should be less than or equal to C only when C is your channel capacity. Do not consider this C as code word. Do not consider it as a code word. C is always your channel capacity. So with C as a given channel capacity, with the M sources always greater than 1, R as your information rate, the Shannon's theorem states that R less than or equal to C is your Shannon's theorem. So for this only, we'll be having an encoding technique such that the output of the information can be transmitted over the channel and with the probability of error that can be minimized. Okay. So the explanation is given. It states that if R is always less than or equal to C, it is possible to transmit the information without any error, even if noise is present, then easily we can do it. Okay. Only the possibility of transmitting an information can occur only if the maximum transmission rate or the maximum information rate R is always less than or equal to the channel capacity C. If that is the case, we can transmit informations without any errors. Though noises will be present, we can eliminate them. So this is what Shannon's second theorem is. So any doubts in this Shannon's second theorem, which you can call it as channel, channel coding theorem. So if you have any doubts till this, you can put it in the chat box. If you have any doubts, put it in the chat box. I'll give you 1 or 2 minutes time for you. Kindly put in the chat box. Symmetric diagram. Yes, what is doubt in the symmetric diagram? You want me to show the symmetric diagram?
Want to explain the diagram, sir?
Symmetric diagram, which you had seen in binary symmetric channel, right?
Yes, yes.
Yeah, binary symmetric. Yeah, just a minute. Is this symmetric channel diagram visible?
Yes, sir.
Okay, can I draw it in a Jamboard
Yes, sir.
such that you can also learn how to do? Okay, I'll take this Jamboard. We are dealing with binary, right? Let the color select. We are dealing with binary. So binary we have 0, comma 1. So x is your input, y is your output. I'll draw it in yellow. Zero and 1. And in y I have 0 because it's in binary. So we have probabilities either. I should write it as 1. Just a minute. Binary will have either 0 or 1. Okay. 1. I will highlight this with an marker such that it will be easier. Okay. So now, first I'll explain you how do I write this P and how do I write this 1. So first we'll define what is this 1 P is. P. P is, we define it as probability of error. Probability of error. So when do we get a probability of error? When our input is 0 and output is 1. I'm giving 0 as my input, but I'm getting output as 1. So means that it is error. So probability. Next is that if I'm giving input as 1, I'm getting output as 0, which is probability of error P. Okay, probability of error. Now what I'm going to do is that what is a non-probability of error? I'll take green color. So if I'm giving 0, I get 0. If 0 is given, I get 0. So 1 minus P. For example, if P value is equal to 1, if P value is 1, if I consider P value as 1, if I substitute that in here, what will I get? 1 minus 1, which is always 0. Okay. So now I take, for again, similarly for 1 as input. So 1 minus P. I think you didn't understand the P concept, so that's what. Okay. So here also, if you take P is equal to 1, what will happen if the probability of error is there? What will happen? This will become 0, such that this 0 is depending upon what? I'll highlight in another color. I'll highlight it in. So 0 depends upon what? It depends upon the input 1 in this case and in this case. This is your corresponding inputs for 0. Similarly, for 1, this is also dependent upon this 0 state and this 1 state. So if the outputs are dependent on the inputs only, these are depending upon the input only, so then we call this type of channel as symmetric. So hence the name binary symmetric. Since we are dealing with channels, it's binary symmetric channel. I hope the diagram for symmetric is clear now with use of Shrikala. Binary symmetric channel. Any other doubts? Let me check in the chat box. Is this clear, Shrikala?
Okay, sir. Clear, sir.
Okay. Shall we proceed for the next topic? Because the next topic goes for another base. So that's what I had given you a pass. So the continuation of the channel capacity theorem. So in short, the channel capacity theorem, which is given as Shannon's theorem, can be expanded to a specific channel. So the channel capacity theorem can be extended to a specific channel, which is Gaussian channel. Always our signals are Gaussian in nature. So since we take Gaussian channels. So this was given by Hartley, Hartly. So the name given as Shannon-Hartley theorem for Gaussian channels. Okay. So the Gaussian channel is being considered. So for this, what is our channel capacity? This is what we are going to find. And most probably the Gaussian channel that is being used is AWGN, additive white Gaussian noise, as you have seen in your random process or in your probability and statistics Gaussian. So the statement is that simple. The channel capacity of a Gaussian noise or a AWGN channel is capacity is equal to B log to the base to 1 plus S by L. So what is this B? B is your total bandwidth in terms of channel. So the bandwidth will be always the summation, so not summation, difference between the higher cutoff frequency and the lower cutoff frequency that we are dealing. So that we get it as channel bandwidth on the frequency spectrum. Then S represents your signal power which is being transmitted, and N is the total noise power which is being present inside the channel bandwidth. And how do we calculate this noise is also given. So B is your bandwidth. The power spectral noise can be easily determined by the noise power N. So how to find N in terms of B is also given. So N is equal to minus integral of bandwidth. So lower cutoff frequency bandwidth B and the higher cutoff frequency bandwidth B. So minus B to B N naught by 2 into the differential function df. Since it is variable with frequency, so df. So where this N naught by 2 is your power spectral density of white Gaussian noise. So then obviously this will become N is equal to N naught into B. N is equal to N naught into B. We cannot substitute that N is equal to N naught into B in this logarithmic function and simplify. We cannot do it. So simply we can expand B as the channel bandwidth, S is the signal power, N is N naught into B. This is your Shannon-Hartley theorem. in terms of Gaussian noise channel. Next topic is the trade-off in the sense relation between the bandwidth and signal to noise ratio. So as you had seen the previous slide, channel capacity of the Gaussian channel C is equal to B log to the base to 1 plus S by N. B is the bandwidth, S by N is the signal to noise ratio. This in terms of bandwidth we are going to find. So the noiseless channel with an infinite capacity can be obtained in two different cases. One is if there is no noise in the channel. We consider that we don't have noise at all, no noise present. So what will happen? Noises. So what will happen? So the first case is that infinite capacity. So when do we get infinite capacity is that when no noise is present. If there is no noise at all, n will become 0. So obviously n will become 0. So substitute n is equal to 0. So what do we get? S by n will be infinite. So one logarithmic function of 1 plus infinite into b will be obviously infinite. So we get infinite capacity. So larger capacity of the channel can be obtained. More information can be added up. But in real practice, we cannot obtain as it is. There is no condition or there is no such a channel which has infinite capacity or a channel which doesn't have noises at all is the state. So the first thing is that noiseless channel has infinite capacity, having channel capacity as infinite, where no noise will be present. So now we consider there is a noise. Now we consider there is a noise with B infinite, or we consider that the noise present in this system is having a limit of bandwidth B. Okay, so then what will happen? So there I'll be substituting n is equal to n0 into B in that case. And as the noises are present with a value of B, the signal to noise ratio decreases due to this noise power. Hence, even if B approaches infinite, even this B value approaches infinite, the capacity doesn't approach infinity. So this can be illustrated as such that when you calculate, you will be getting logarithmic function of that B infinity. You will be getting 1.44 in terms of n0, signal to power ratio. So the upper limit will be always given as for an infinite bandwidth channel capacity, C infinity is equal to limit B tends to infinity, which is always 1.44 times S by N0. So this is your relation for bandwidth and signal to noise ratio for infinite bandwidth or having a limited capacity. So these are the trade-offs between bandwidth and signal to noise ratio. In the next, we will see a trade-off between rate and bandwidth for the channel capacity. So consider a spectral system having a signal power S, which is resembling in terms of energy bits. So the channel capacity C can be obtained in terms of energy transmission, and energy transmitted per bit is represented as EB, E suffix B. The channel capacity is represented in terms of bits per second. So the relation we get S is equal to EB into C. So yes, so S is your signal power. So we know this equation just now. We are saying C is equal to B log to the base 2 1 plus s by n, the previous equation. Trade off between capacity C. So substitute that, rearrange, bring this B that side. C by B is equal to log to the base 2 1 plus EB by n naught into C by B. So rearrange it, take exponential form such that you can eliminate this base 2, rearrange, you will get C by B is into log to the base e power 2, which is log to the base exponential of 1 plus EB by n naught into C by B. So simplify this equation, which I am encircling. Simplify this log to the base 2 log to the exponential e power 2 C by B is equal to log to the base exponential 1 plus EB by n naught C by B. So remove this log exponential, we get 2 power C by B is equal to 1 plus EB by n naught into C by B. So I want only EB by n naught. So which is energy bit per noise. So EB by n naught, determine only that. EB by n naught. So if I want to find that, rearrange it, we will be getting 2 power C by B minus 1 divided by C by B. So this is a relation for determining signal to noise ratio. Signal to noise ratio is always EB by n naught. EB by n naught is your signal to noise ratio, which is 2 power channel capacity divided by bandwidth minus 1 divided by channel capacities ratio and bandwidth ratio. More sophistically, we can rewrite in terms of efficiency also as in this equation. As in this equation, EB by n naught is equal to 2 power RB by B minus 1 divided by RB by B. So where RB is written in terms of C, channel capacity. So next is a diagram that you can see. The diagram is drawn signal to noise ratio versus rate bandwidth. In x-axis we have signal to noise ratio EB by n naught. In y-axis we have rate bandwidth RB by B. So you can see that graph. You can see this graph. There is a curve, but different values being plotted. This graph RB is equal to C is the graph, which is a dark line color. Okay. So in the region where RB is equal to C is your capacity boundary region. Capacity boundary region. Beyond this, we will have two cases. One is RB greater than C, another one RB less than C. If RB is greater than C, what will happen is that this region will be having more errors. In RB greater than C, there will be more errors. So these are the dots and points which shows regions with different probabilities, rate of bandwidth with respect to the signal to noise ratio, how many bits are being affected, number of bits being affected. So whereas when you see RB less than C, in this region, none of the bits are being affected. So this region we call it as error-free region. The region which is RB less than C is error-free region. So error-free transmission can be possible in this. Whereas in this, always there will be errors. Okay, there will be certain that only errors will be present in RB greater than C. If the number of bits that have been transmitted are in excess of the channel capacity, obviously errors will occur. So this is a illustration in this diagram. So you can write. So you can write the equation: capacity of infinite channel capacity 1.44 EB by channel infinite divided by N naught, or EB by N naught is equal to 1.44. You can find easily. So which is 0.693. Okay, this I'll show you here. So here is your value. So the Shannon's limit represents your region of convergence. Shannon's limit. Okay, which is approximately EB by N naught minus 1.6 dB. Sorry for moving this line. So if we calculate this EB by N naught, logarithmic of that 0.693, we get minus 1.6. So this is your Shannon's limit. So you can see that minus 1.6 dB in S bar and ratio. So beyond this, we have no errors, which we call it as error-free transmission. Below this 1.6, we have much more errors. So minus 1.6 dB in signal to noise ratio is your Shannon's limit. And for this, the capacity is 1.44 signal to noise ratio. So this is what being plotted in the diagram. Okay. And also we can write the probability of error for this system. We can write the probability of error for this system as probability of error PE is equal to 1. When do we get an error? We get an error only when RB is greater than or equal to C. And we don't get an error which is 0 for RB less than C. And so this is also a part of your Shannon's coding theorem. Shannon's second theorem or channel coding theorem. If it is RB greater than or equal to C, definitely there will be an error. Probability of error will be there. If RB is less than C, we will never get an error. We can easily retrieve the signals. So in today's session, all these things we had seen, and these are the references. References same, information and coding, introduction to information theory, same authors I referred. So any doubts? Yeah, Pawan Chandra, just now I completed. It's enough for today, sir. Yeah, it's over. It's over for today. I would like to give you some 2 or 3 minutes. Relax yourself and I'll take the attendance. So in today's class we had covered the binary symmetric channel, mutual information, differential entropy, discrete memoryless source extension, channel capacity, channel coding theorem, and the trade-off between bandwidth and signal to noise ratio. So in the next class, depending upon all these things, we'll be solving problems. So as per request given from Pawan Chandra, I think so, yeah, Pawan Chandra. Today's presentation is over. I'll give you 2 or 3 minutes such that you can relax. And, Okay, I'll stop the recording since